Okay, so whenever we have a charge moving through a magnetic field, it will experience a force. And we can calculate the magnitude of that force. It's going to be this. It's going to be the charge. It's going to be the velocity of that charge times the magnetic field times the sine of the angle theta. This comes about if you're in Calc 3. I know most of you aren't, but if you've ever had Calculus 3 or vector calculus, it comes about because it's equal to the cross product of V and B. Right? You might see this elsewhere. I'm going to have a couple of links for the right-hand rule and some things that we'll see. And this is all in the context of the right-hand rule. And for the right-hand rule, the magnitude of this is given by the constant times the magnitude of the first vector times the magnitude of the second vector times the sine of the angle between them. So this is, in definition, what a cross product is. The cross product is the product of two vectors, the magnitudes of two vectors, that are perpendicular to one another. And that's where this comes about. So if I were to look at V here, it's in this direction, and B sine theta would be in this direction. That's the y component of the B vector. And so it's the product of two perpendicular vectors. All right. Now, the result of this perpendicular vector is going to be orthogonal to both vectors. So in this case, if V is in this direction, and our B sine theta is in this direction, then the vector F is going to be coming out of the page, coming towards you. And so you see it's orthogonal. That means perpendicular to both vectors. We'll see that again in just a bit. Now the SI unit for the magnetic field is the Tesla, T-E-S-L-A, also capital T. And of course, this was after the famous scientist Nikola Tesla, after whom the electric car is named after. Also, there was a movie, I think it was called The Prestige, that was about him and some of his work. And we'll see him a little bit later. He was pretty crucial to the founding of our electrical system that we currently use in the United States and around the world. Sometimes the magnetic field is expressed in Gauss. I won't use this, but sometimes you might see it. And a Gauss, 1 Gauss is equal to, or excuse me, 1 Tesla is equal to 10 to the 4th Gauss. That's 10,000 Gauss. Okay, we're going to use the right-hand rule to determine the direction of the force, and we'll have a number of different practices on this. You'll see it in the concept test and in the online quizzes and what have you, as well as if you look back at the old exams, which I recommend that you do, you'll see this. So it'll make a handful of questions on your next exam. I'll also have a link on the website to an alternate explanation of this. So if you're not following this, just why don't you try reading through this other explanation of the same thing, and then practice. So we're going to use the right-hand rule. This will allow us to determine the direction of the force. Let's see how I can draw a hand. Here's a hand. That's the pointer finger. All right, that's a very large, it looks more like a foot, doesn't it? There's the thumb. All right, we're going to use the right-hand rule to determine the direction of the force. Now, the fingers of your hand, your right hand, go in the direction of V. All right, so our vector V will be in the direction of these very toe-like fingers. But the fingers of your right hand go in the direction of V. You're going to either fold your fingers towards the magnetic field, or you can think about it in a different way, or you can let the magnetic field come out of your palm. Either way is okay. So here, I'm going to use a symbol here for my magnetic field. We'll get to this in just a second, but my magnetic field here is coming out of my palm. All right, so I have my V to the right, and my magnetic field is coming out of my palm. And so now, to find the force, the direction of the force is given by the thumb. So my force now is in this direction. All right. We'll do a number of different examples of this. If you're having trouble with this, it might be useful for you to come see me. I could sit down with you for 5 minutes and we can go over this a little more. Let's do a couple more details. Now, this assumes that the charge is positive. If the charge is negative, then you just take the opposite direction that's given by the right-hand rule. We assume that the charge is positive to begin, then we find the direction of the force or whatever it is that we're finding. But if the charge is positive, we find it, and then we take the opposite of that. We're going to use some symbols. I've already used one of these to denote coming out of the page. This was the symbol that I used to come out of the page. If you've ever had an arrow that's coming towards you, this is what it looks like. This is the point of the arrow, and then we just put a little circle around it. Sometimes you won't see the circle. Sometimes we'll use just a dot. Like, for example, if I have a region with a magnetic field, I'll just use a bunch of dots. And that just means that it's coming out of the page. So that symbol is out of the page. That's also what we'll call the plus Z direction, or you might see it the plus K direction. Into the page, we'll use a symbol like this. And this is like an arrow going away from you. You know, an arrow has a pointy end, but then it has the fletching. All right. And so that's like the fletching on the back of the arrow. This would be going into the page. Sometimes if we're going into a region, we won't use the circle. We'll just do it like a bunch of X's like this. And that would show a magnetic field, a region with a magnetic field that's going into the page. Let's do a couple of these examples. All right, remember, let my fingers go in the direction of V, of my right hand. My magnetic field comes out of my palm. And so what is the direction of the force on this one? All right, it's going to be the direction of your thumb. Now, first of all, I know that, this is in the Y direction, this is in the X direction, so my force has to be in the Z direction. So is it plus or minus Z? And that's where you use the right-hand rule. Fingers in the direction of V, they fold towards B, or you can imagine that B is coming out of your palm. And in this case, your thumb is going to be pointing out of the page, and so the force is out of the page. Here, I have V going down, so your fingers of your right hand point down, and then you orient your hand so that your palm is pointing into the page, because my magnetic field is into the page here, it's away from you, and so that gives a force that is to the right. All right, one more. Fingers out of the page, and then you orient your hand so that your palm is pointing down, or pointing towards you in this case, depending on how you're holding your hand. And so my force is going to be in this direction. Now, we can use these oppositely, all right, where I don't give you the magnetic field or I don't give you the velocity, but instead I give you the force and something else. And in these cases, you just work backwards. So here, I let my fingers go in the direction of V, and then my thumb points out of the page because of this force vector, and then my magnetic field is in this direction, out of my palm. Here, fingers into the page, my thumb to the left, and my magnetic field is in this direction. And here, I will take my thumb down, my palm pointing so that it's out of the page, because that's my magnetic field. My thumb down, my palm out of the page, folding my fingers out of the page, and so my velocity vector is to the right. That's a hard one. That's a sort of a contortionist one. Okay? Right-hand rule can be very useful. It allows us to see 3 dimensions in a more physical way, and we're dealing with orthogonal vectors that are on a right-handed coordinate system. All right, so they always look like this. They're always orthogonal to one another. And our so in this case, like for example, this would be V, this would be B, and this would be F. So I always have these orthogonal vectors in a right-handed coordinate system. There are a few practice problems here for you to try out. There are a number of different practice problems actually in the old test and later in the online quizzes that you'll see. On this one, you push these copper wire through a magnetic field as shown. Let's consider it in a sort of different way. Let's say that my wire is moving with a velocity in this direction. And so you can imagine that there are charges here. All right. We're going to assume that it's conventional current. That means that there are positive charges moving. And so what is the direction of the current in the wire? I have these positive charges moving in this direction through a magnetic field. What is the direction of the force that they feel? Do they feel a force that is up, or do they feel a force that is down? We will pause there, and when I post this online, I will leave a link for an additional explanation of the right-hand rule.